So we did step 2, and now we'll move on to step 3 here. And so you got x equals 2 point, what was it again, Joanna? 2.219 times 10 to the negative 12. Did you use the simplifying assumption? You use the solver on the calculator?
I did simplifying assumption. I got the same.
Yeah, in this case, the simplifying assumption and the solver are going to give you the same answer because the percent change is so small. And so this is fine. So the hydronium, we end up with 2.219 times 10 to the minus 12 molar, which is very small. And then let's see how much additional hydroxide we've gotten. So this is our running total. From steps 1 and 2, we got a cumulative hydroxide of 0.004506.02272. And now in step 3, how much more hydroxide are we going to add? And so this is going to be 11 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 11 zeros, and then a 2219. And so let's add 4 more zeros there. And so we're going to end up with 0.004506.022722219. Did we add much?
No.
No. Is this going to screw up the double check we just did in step 2? No. Is it going to screw up the double check we did in step 1? No. And so even with this tiny addition, those should still be in equilibria. And so this will be our final hydroxide concentration. Now, take a look at this. Even though there were 3 steps that contributed hydroxide, the first step by far contributed the most hydroxide. The second step barely added any hydroxide to that. And the third step even added even less hydroxide. And so if you're only interested in pH, was it necessary to do step 2 and step 3? If you're only interested in pH, it wouldn't have changed anything because the bulk of the hydroxide was produced in step 1. Here, this is step 1. The only time step 2 would impact that is by looking at the K value. If I look at the step 2, the K value here is 10 to the minus 8. If step 2 had a bigger K value, like 10 to the minus 2, I would worry about it. But if step 2 has a K value like 10 to the minus 3, 10 to the minus 4, or smaller, then I wouldn't worry about it if I'm only interested in pH. If I'm interested in the inventory, then I have to do everything. So the final inventory is this. Let's go ahead and summarize the final inventory. The final inventory is this. If I had a solution that's labeled 0.10 molar sodium carbonate, I actually have a lot of species in there. The species that's going to be in highest concentration will be sodium ion. Sodium ion, there's going to be twice as much sodium as carbonate. So I'm going to have sodium ion at 0.20 molar. The next most abundant species will be carbonate. And so if I go to carbonate, it's at 0.09549 molar. And so carbonate is at 0.095. Just throw in one more digit. We're only allowed 2, or actually 1 maybe in this case. So carbonate's the next most abundant. Then what's the next most abundant after that? So carbonate, this is the end of the line. Bicarbonate goes through here, then bicarbonate continues to here. Bicarbonate's not the next most abundant. We'll just put it in here. Bicarbonate is going to be at 0.00450 molar, slightly less than that. Carbonic acid, this is the end of the line for the carbonic acid, and so we're going to get some carbonic acid in here. The carbonic acid concentration is very low, but it would be 2.27 times 10 to the minus 8 molar. And so a tiny bit of carbonic acid will be found there. The hydroxide continues. This is not the end of the line. Hydroxide is going to be out here. You're going to get a tiny bit more hydroxide in step 3. And so in the end, the hydroxide comes out to 0.00450 molar. And so this is slightly more, this is slightly less. So this is just slightly less, this is just slightly more. And they aren't exactly the same. And so this would be the, not there, this would be the end line of hydroxide. And then we actually form some hydronium. You know, the definition of basic solution is that the hydronium concentration is less than the hydroxide. And that's exactly the case here. So we'll have a tiny bit of hydronium in here because we can't stop waters from colliding. So the waters are going to produce the hydronium, even though this is a base solution. This is going to be 2.21. 2.21 times 10 to the minus 19 molar, which is very small. And so if I have a beaker that's labeled 0.10 molar sodium carbonate, these are all the species I predict that are in here. Now the pH is going to be based on this. Here from the hydroxide, this is the equilibrium, the total equilibrium hydroxide. So the pOH will be the negative log of the total hydroxide concentration. We figured out the total hydroxide from adding all 3 steps, but it turns out only step 1 was the major contributor. And so you see I even rounded off. When I rounded this off, you know, step 2 and step 3 are missing, I mean, because it made no impact. And so this is going to be negative log of 0.00450, and so our pOH comes out to 5.40. 5.400.
Yeah, 2.3.
2.3. 2.3, give me a couple more digits. 2.347? All right. And therefore the pH is 14 minus that, and so the pH is going to be 11.653. The pH is fairly high, meaning that sodium carbonate is fairly basic solution. And sodium carbonate is a decent base, being 5.5% hydrolyzed. You know, it's not a strong base. A strong base would be closer to 100% hydrolyzed, but it's not bad. It's a decent base, sodium carbonate. And so this is what we call the inventory here. Sometimes I'll ask for the inventory and the pH. Sometimes I'll only ask for the pH. If I only ask for the pH, you could save yourself a lot of time by just doing steps 1 and possibly step 2. And because each successive step, now the steps you have to do in this order, you have to start with the largest K and then work your way down to the smallest K. All right, we'll take a break and then we're going to start the lab after that.